Today's lesson will be over 4-4, where we will be solving nonlinear systems of equations. Our essential question will be, how do you solve systems of equations in two variables in which one equation is linear and the other equation is quadratic? So our first definition today is going to be a nonlinear system of equations. And this means it's a system in which at least one of the equations is nonlinear. For example, a system that contains one quadratic equation and one linear equation is a nonlinear system. So remember, when we're graphing something that's linear, it's always going to graph a line. So a nonlinear system is something that will not graph a line. In the pictures below, it says a system made up of a linear equation and a quadratic equation can have no solution, one solution, or two solutions shown below. This picture set does not have a solution because they never intersect. The solution is the point or points at which the quadratic equation and the linear equation intersect. In this second picture, the line and the parabola intersect only at one point, making one coordinate the solution. And in this last picture, our parabola and our line intersect at two locations, meaning we have two solutions or two coordinates at which they intersect. So today we're going to look at three different methods in which we can solve a quadratic and a linear system of equations. The first method is by graphing. So we're going to start by graphing each of these equations. If you notice, the first one is a quadratic equation, so it should graph a parabola. One way we can graph this parabola is by using an XY table and identifying what our vertex is. We've talked about several different ways of identifying our vertex. The quickest way is to take x and set it equal to negative b over 2a to find our x-coordinate of our vertex. When we do that in this case, we're going to end up with negative 4 divided by 2 gives us negative 2 as the x-coordinate of our vertex. When we plug in negative 2 for our x values and solve for y, we would end up getting our y-coordinate for our vertex as negative 1. So we know our vertex is going to lie at negative 2, negative 1 for that parabola. Now I can find some x values that fall to the left and to the right so that I can graph it more efficiently. So negative 3 and negative 4 fall to the left, negative 1 and 0 would fall to the right. So plugging in each of these x values, we can solve for the y-coordinate that matches with those. Starting with negative 3, if I plug in negative 3 for each x location, that would give me 0 as my y value. And if I plug in negative 4, that's going to give me 3 as my y value. Plugging in negative 1 gives me 0, and plugging in 0 gives me 3. So I'm going to plot these points on my graph to the right. So here's the start of my parabola. Okay, now the next equation is a line. It's a linear graph. So when we graph lines, we think about it in the form of y equals mx plus b, where m is our slope and b is our y-intercept. Last year you talked about how to graph these. We start by graphing our y-intercept at positive 3. And from there, we use our slope, in this case is 1, and slope is rise over run. So we rise 1, run 1, rise 1, run 1. We can also go backwards, so down 1, left 1, down 1, left 1, down 1, left 1, and we can keep going. So here is our linear equation y equals x plus 3. Now, to find the location at which they intersect, those would be our two solution points. So the location at which they intersect is -3, 0, and at 0, 3. These would be our solutions to the system of equations, two ordered pairs. Why don't you take a second to try this one by graphing. So hit pause and see if you can graph the two equations and find their intersection points. Okay, so hopefully your graph looks like this. Remember, we find the x-coordinate of our vertex by taking -b over 2 times a, and that would give us +2 as the x-coordinate of our vertex. We find coordinates that fall to the left and to the right, plug in those x values, and that gives us our y values to graph our parabola. Then we graph our linear equation, which has a slope of 1 and a y-intercept of 1. So the locations at which they intersect are 1, 2, and 4, 5. So this solution set, or this solution for this system of equations, would have two intersection points, 1, 2, and 4, 5. Now, our next method for solving a system is by using substitution. And I've given you a reminder here that the substitution method is a good choice when the equation is already solved for a variable, or both equations are solved for the same variable, or a variable in either equation has a coefficient of 1 or -1. So you've used the substitution method before, but it was just solving a set of linear equations. Today we're going to apply the substitution method with a linear and a nonlinear equation. So we would use the substitution method in this set of equations because they're both solved for the same variable. So what we're going to do is we're going to substitute a value into the other equation for which y is equal to. So since y is equal to both of these equations, we may set our two equations equal to one another, basically replacing or substituting for the value y. So when we get here, all the variables are the exact same, and we want to solve this quadratic equation. So I'm going to solve by trying to factor. I'm going to get everything to the same side of the equal sign, trying to keep my squared term positive. So I'm going to add 3x to both sides, and I'm going to subtract 3 from both sides. When I do that, the left side cancels out to 0, and that leaves me with x squared plus 2x minus 8. So I want to check to see if this quadratic equation is factorable. If it is, that may be the quickest method as opposed to solve by completing the square or solve by using the quadratic formula. So this is factorable. Our factors are going to be x plus 4 and x minus 2. Solving for x, we take our factors and set them equal to 0 and solve for x, giving us x values of -4 and +2. Now, we're not done because we want to find the intersection points for this linear equation and this quadratic equation. So I know I should have two locations at which the parabola and the line intersect because I have two different x values. So one x value is going to be -4. The other x value is going to be +2. I have to now figure out what the y value is going to be for each of those coordinates. So the easiest way to do that is to take your x values and plug them back in to your original equation and solve for y. The greatest thing is, it does not matter which of these equations you choose to plug it into. So I like to work smarter, not harder. It's easier for me to plug into a linear equation because I only have to replace one x. So first, plugging in -4 for x, my solution for y would be 15. So the coordinate -4, 15 is one intersection point. To find my other coordinate, I'm going to take 2 and replace it in that same equation. So that ends up giving me -3. So the other location is going to be 2, -3. So our solution set of coordinates is listed here. -4, 15, and 2, -3. So how about you hit pause and try using the substitution method to solve this system of equations. Remember, since they're both equal to y, all you have to do is set the two equations equal to one another. Okay, so let's check your work. Remember, we set our two equations equal to each other. We get all the variables on the same and constants on the same side of the equal sign. When we do that, that should end up giving us 0 equals 3x squared minus 3. At this point, you may choose how you solve. You could have solved by taking the square roots in this problem. You could have solved by quadratic formula, or you could have solved by factoring. I chose to solve by factoring, so I factored out my GCF. I was left with a difference of perfect squares, so I factored it again. Then I took my factors and set them equal to 0. Remember, 3 does not equal 0, so that's an extraneous solution. And so my two solutions for x would be -1 and +1. So I set up my ordered pairs to the right and found my y coordinates by taking each x and plugging them back in to the equation listed to the left. And again, you may choose to use either of these two equations, but I chose to use the linear one because it works out faster. But if I chose to plug in -1 into the quadratic equation, it would still give me 7 as my y value. And same thing if I chose to plug in 1 to my x's in my quadratic equation, it would simplify out to give me 1 as my y value. Okay, last method is the elimination method. The elimination method is a good choice when both equations have the same variable term with the same or opposite coefficients, or when a variable term in an equation is a multiple of the corresponding variable term in the other equation. So if you notice here, our equation looks a little bit different because our linear equation has multiple variables on the left-hand side. So I'm just going to rewrite the two equations where they line up appropriately, where our equation symbol lines up appropriately. So 3x minus y equals 1. And rewriting my my second equation leaves me with y plus equals x squared plus 4x minus 7. So all I did was kind of line up like terms on the left side of the equation and the right side of the equation. So the elimination method works here because if you notice, our y in our first equation is negative and our y in our second equation is positive. If we were to add these two equations together, our y's are going to eliminate one another. That's the elimination method. We want to eliminate something or get rid of it. So what that leaves me with is 3x equals x squared plus 4x, and then combining like terms, minus 6. And now we're pretty much at the same step as to where we would start with substitution. Once the equations are set equal, solve the quadratic. So I'm going to move 3x to the other side by subtracting. They cancel and leave me with 0 equals x squared plus x minus 6. So I check to see if this is factorable, which it should be, or you can use solve by completing the square, or solve by the quadratic formula. Factoring is just a little bit faster. So our factors that multiply to give us -6 and add together to give us +1 would be +3 and -2. So solving for x, we get x equals -3 and x equals +2. So writing down our ordered pairs, and taking and plugging back in. We can plug back into any equation, but we want to solve for y. Since this second equation is already solved for y, it may be easier to choose this one. So I'm going to plug in x as -3 into that equation. And when I simplify that out, I should get y equals, let's see, I think that's -10. And then when I plug in my value of 2 squared plus 4 times 2 minus 7 leaves us with 5. So these would be our solutions or our intersection points for the quadratic equation and the linear equation. Okay, now on this next example, if you notice, if we were to line up our two equations, what happens is when we line up our equations, our y variables, one is -2 as a coefficient, the other has a +1 as a coefficient. If we were to add these sets of equations together, they wouldn't eliminate. So we've got to multiply this entire equation on top by a number that would cause y's to eliminate if we were to add the equations together. So that number would be +2. So basically, I'm just going to rewrite this whole equation set again. So we would have 2y equals 2x squared plus 2x, oops, forgot to distribute. 2 gets multiplied by each piece. So that would be 2y equals 4x squared plus 2x minus 2. My second equation would stay the exact same. X minus 2y and then equals 6. Now I have opposite coefficients in front of my y term. If I were to add these two equations together, my y's will now eliminate. I will be left with x equals 4x squared plus 2x plus 4. Solving like before, I'm going to subtract over my x. That leaves me with 0 equals 4x squared plus x plus 4. So now we want to decide, is this factorable? Well, if I try to factor this, there is no common factors that multiply together to give me 16 and add together to give me 1. So I'm going to use the quadratic formula. Our a value will be 4, our b value will be 1, our c value is also 4. So that gives me the opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Continuing to simplify this, this will give me -1 plus or minus the square root of -63 all over 8. And if I go further, that would give me -1 plus or minus 3i root 7 all over 8. So, here's the issue. My x value is an imaginary number, meaning that we cannot see the location at which these two equations would intersect. So at this point, we would say there is no solution because our location for our x values is an imaginary number. So these two equations would not intersect. Like in our visual slides from the very beginning, it would be a situation where the parabola and the line do not intersect. Please make sure to note if you have any questions on this example to ask them in class tomorrow. Okay, last set should be able to be solved by the elimination method. Hit pause and try this one on your own. Okay, so our y's should eliminate. We get all of our terms on the same side. It's factorable. We get our solutions as x equals 3 and x equals -1. And we plug those back in to find our y coordinates that match. So you should have the solutions 3, 4 and -1, 4. The last example is an application question. So it says, an elevator is rising at a constant rate of 8 feet per second. Its height in feet after t seconds is given by h equals 8t. At the instant the elevator is at ground level, a ball is dropped from a height of 120 feet. The height in feet of the ball after t seconds is given by h equals -16t squared plus 120. Find the time, or t, it takes for the ball and the elevator to reach the same height. So we have these two equations, one linear, one quadratic. They're both solved for h, so hopefully you identified the best method to use would be the substitution method, setting our two equations equal to each other. Once you set these two equations equal to each other, I want you to solve for t. Hit pause and do that now. Alright, so hopefully when you got everything to the same side, you factored out your GCF of -8, and then you either did factor by grouping or factor using the magic box to get your factors of 2t minus 5 and t plus 3. When we set those equal to 0, remember this is extraneous, we get t equals 5 over 2 and t equals -3. Now remember, we're talking about time, so we're talking about seconds. Typically, when we're talking about real life seconds, we would say this is t equals 2.5 seconds instead of writing it as 5 over 2. And then we don't deal with negative seconds in real life. So in this situation, -3 does not make sense. So our time is going to be 2.5. As an ordered pair, our time would be our x value. And our height from the original is our y value. So what's happening is find the time it takes for the ball and the elevator to reach the same height. They would reach the same height after 2.5 seconds. But what if I asked you what that height was? We would take 2.5 seconds and plug it back in to one of these two equations and solve for h. Well, 8 times 2.5 would give me 20, and our units for height were feet. So they would be the same height 2.5 seconds, or after 2.5 seconds, and they would reach the same exact height at 20 feet. All right, make sure to write down any questions you have from this video and ask them tomorrow in class.